The research that I am presenting is the same that I presented at the IEEE International Intersonic Symposium at the beginning of September. Three-dimensional evaluation of microvascular networks using contrast-enhanced ultrasound and microbubble tracking. Evaluating tumor microvascular networks with use of contrast-enhanced ultrasound imaging and a transducer to collect data that produces 2D images inherently has limitations, as tumors exist in volume space. A process was defined by first injecting intravascularly microbubbles as a contrast agent into a developing chicken embryo. A transducer was then scanned over a region of interest to capture a volume of data with 1,000 sequential images at each of the 8 tissue cross-sections and a step size of 0.09 millimeters between them. The data was processed initially with a singular value filter to remove any stationary clutter artifacts, and localization was performed to define the microbubble centroids. Velocity maps at each tissue cross-section were created by validating microbubble locations through a nearest neighbor search with 3 criteria. The first was that the microbubble must show the same change in direction along the x-axis throughout the entire track. This means if the first pair of microbubbles show a positive change in direction, this must be true along the remainder of the track. The second criteria defined was that the microbubble must be tracked through 5 or more sequential frames. And the last condition for microbubble tracking was an established threshold of a maximum expected blood velocity in microvasculature with a diameter of less than 200 micrometers. Validated microbubble locations were placed into a new image with the values being the Euclidean distance between locations. If more than one microbubble was detected at the same location, the final value was represented by the mean distance. Finally, the distances were multiplied by the frame rate to create the velocity maps at each tissue cross-section. These planar maps are combined to produce a 3D super-resolution ultrasound super-resolved velocity images. This process is detailed in Figure 2 on the poster, and in Figure 1 shows the region of interest from the original image. The results are representative 3D super-resolved microvascular velocity map reconstruction from the developing chicken embryo and is shown in Figure 3, created from a sequence of contrast-enhanced ultrasound imaging. It has been shown previously that a pair of linear array transducers placed orthogonally can be used to obtain a 3D super-resolved velocity map. The method introduced in this study overcomes the orthogonal limits and potential clinical obstacles by using a single linear array transducer and contrast-enhanced ultrasound imaging-based microbubble tracking. To make improvements on this study, a more robust microbubble tracking algorithm could be used to increase the ability to follow microbubbles and throughout a larger region of interest. Further directions would be to implement this method with previous studies that have expressed limitations due to being confined by data acquired from 1D linear array transducers. In conclusion, this research introduces a method for creating 3D super-resolved velocity maps using a preclinical ultrasound scanner and mechanical translation of the imaging transducer.